Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our thermodynamics lecture series. And today we are going to look at ternary phase diagrams. That is, phase diagrams for three-component systems. We have been talking about two-component systems, but today we'll talk about three-component systems and see how we can represent those systems in a diagram. So we will look at ternary systems. These are three-component phase diagrams. Now, we have been used to working with two-component phase diagrams where we developed several principles. We saw that when you are in a two-component system, for example, we looked at their temperature composition diagrams, and we have looked at single-component diagrams where, for example, we had even the phase diagrams for things like carbon dioxide, water, helium, and the likes. And so today we are going to look at a three-component system. Now, the first thing which we need to deal with is what is our phase rule when we are dealing with these ternary systems or multi-component systems. So the first thing we do is develop the expression for the phase rule. What is phase rule? Remember we said phase rule is F is equals to C minus P plus 2, where F is the variance of the system, C is the number of components, P is the phases. F is the variance of the system, or number of degrees of freedom, C is the components, and P are the phases. Now, we say that this 2 plus 2, the 2 represents the temperature and pressure variables. So, what are we saying? For a three-component system, we will have the variance F is equals to 3 components, 3 minus P plus 2, and that is 5 minus P as the phase rule for that three-component system to start with. If we keep the pressure constant, remember, then we have plus 1, so we will have 4 minus P. If we keep temperature C constant, it will be 4 minus P. If we keep temperature and pressure constant, it will simply be 3 minus P. Note, if temperature or pressure kept constant, then the new representation for the phase rule will be pressure constant will be C, that is 3 minus P plus 1, which will be 4 minus P. Similarly, if you keep temperature constant, it will still be 3 minus P plus 1, that will be 4 minus P. And if you keep temperature and pressure constant, the phase rule will be 3 minus P. Very important for you to note that. So always know what kind of constraints have you put in the system. Is it isothermal? Is it isobaric? And so forth. Now, how do we represent the three components in a system? Suppose the three components are A, B, and C. Suppose the three components are A, B, and C. How do we represent them? That is where we come to the Gibbs-Roozeboom Triangular diagrams. This triangle is purely an equilateral triangle, and you know what an equilateral triangle is, has equal sides, and the degrees is 60. Now, let us look at a situation where we have those three components that we call A, B, and C. We have those three components A, B, and C. We represent them with Gibbs-Roozeboom triangular diagrams. And I said, one, the triangle is an equilateral triangle. Equilateral triangle. And what are the features of an equilateral triangle? You know that an equilateral triangle, the sides are equal, and of course these angles, you know, are 60 degrees. 60 degrees. Always know that. All those angles are 60, the sides are equal. Now, let us represent those 3 points, the 3 components, in a triangular diagram. So we have the triangular diagram, component A, component B, component C. Now they are all at the apices of the triangle. See, there's an apex, there's an apex. Look at this triangle as it is. There's an apex relative to these two. There's an apex relative to these two. There's an apex relative to those two. Now, the significant thing here is that at the apex here, this represents 100% C. At the apex, that direction, this represents 100% B. From this direction, this apex, that represents 100% A. So, if now we are talking of 100% of C, 100% of B, 100% of A, how do we represent the other percentages? First of all, think of it this way in your mind, that you have a straight line. That is 0. 0% C, this point. And that's 100%. So we can draw segments, this, so that we have up to 100%. Let's hope they will be 100. That will be 20, 10, 20, 30, 40, 50, 60, 70, 80, 90. So we'll stop at that. So that will be 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%. And the same is done for these other portions here. So again, this one here, we can again divide them into segments: 10%, 20, 30, 40, 50, 60, 70, 80, 90, 100% of B. And the same for A. Same for A. Have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%. Now, we now know this triangular diagram. Now, suppose I want to represent, you take a state point here. Let's take a state point which is 20%. Let's call that state point P. That state point P has 20% of A. Composition is 20% A, and not 20% A, 20% C. And going to the apex here, A, let's say it's about, what did we get it? That's about 10, 20, 30, 40. So at BA should be 40% for A, and for B, that is B, this is for C. That's state point P, state point P. For B, definitely it is 20, 40, that's 60. So where is our B? B is this line. So that line should be about 20, 40, 60, another 40%. So if you draw the diagram to scale, then they should completely fit that configuration of percentage which we have there represented by the state point P. Now, if we have another state point, let us say there's another state point, let's call that state point M. You have two state points, let's call state point M. So at state point M, what will be the percentages? Let's use this side. At state point M, what will be the percentages? At state point M, state point M, okay, let's look at it. State point M, we are seeing clearly that for A it's about 30%. A is about 30%. For B, we are here. B is about another 20%. And for C up there, it says that should be about 50% if it is drawn to scale. C. Now, what about a point, state point? If you have a state point lying somewhere between the line joining state points A and B, that tie line there. Suppose there's a state point here, Q prime. Now, the important point to note there is that if there's a state point, Q prime, lying between state points M and P, then the value of that Q must be a composition on this line here. The value of the composition of that state point will be a composition on some point in this particular line, MP. So note that for the state point Q prime, the value composition will be on the tie line, joining state points M and P, joining state points M and P. Very important for us to note. Well, that the composition will be some point of the state point Q prime will be some point lying on that line there. In the same way, if we have now, let's remove that. If we have now 3 points, that's 3 state points, let us call that state point X. So we have state point M, P, and X. Then the composition of that mixture of M, P, and X will lie somewhere in this triangle here. Let's call it Z prime. So in that case, if you have state point, a mixture having composition M, a mixture having composition P, and another having composition X, then the resultant mixture will have its composition within that triangle MPX. Let's write that down somehow. Just note something that for state points, for a mixture, so for a mixture M, P, and X, resultant composition must lie in the triangle itself, in the triangle MPX. Must lie within the triangle MPX. That's a very important point to note. The other point is, if we have our triangle for representing the compositions A, B, and C, and you join the apex C, then all compositions on this line along the apex C, let us call this M prime, that is M double prime. The compositions here, M prime, M double prime, M triple prime, these compositions which you'll have at these state points, M prime, M double prime, M triple prime, will all have A and B in the same ratio. All will have A and B in the same ratio. And you can show that from the principal theory of similar triangles. So what does it mean? If we draw a perpendicular line from these points, perpendicular line, 90 degrees, this point, let's call that K prime, K double prime. Let's call this P prime, P double prime. Note that we have drawn lines perpendicular to this main line representing the state points, and based on the theory of similar triangles, which is an important mathematical concept, we will see that MC, segment MC, M double prime C, this M double prime C over M prime C, that segment must equal, that segment MC must, M double prime C must equal M double prime K double prime and M prime K prime segment, that one. And we have double prime, sorry, there. Then the other one will be M prime C divided by, where we have, where are we? We have M prime C divided by M, let's start with M double prime C divided by M prime C, that segment. That again also will be M double prime P prime, P double prime over M prime P prime, the segments, those segments there. And so we are seeing both are equal, so these two are all equal, so these are equal. Therefore, M double prime, K double prime over M double prime, K prime is equals to M double prime, P double prime over M prime, P prime. So, if we have M prime, yeah, not double prime, we have M prime. So, if we rearrange this, we have M prime, P prime over M prime, K prime, that segment, M prime, that would be M double prime, P double prime over M double prime, K double prime. So those quantities are in the same ratio. That is M prime, P prime, M prime, P prime, M prime, K prime. This ratio to that ratio is the same as M double prime, P double prime, and M double prime, K, M double prime, K double prime. We have there, so we have M double prime. Where are we? We have M, P. We want to have that singular M, P prime. That is M prime, P prime, M1, M prime, K prime, as being equal to M double prime, P double prime, M double prime, K double prime. Then the same ratio, this ratio to that, length of that segment and that segment, that ratio is the same as this ratio, and it will be the same as this ratio here. Let's call that Z1, Z prime, and Z prime here. It will also be in the same ratio as M double prime, Z prime, double prime, M double prime, Z single prime. And even if you take another state point here, just at right angles, again, you can call it M triple prime, 1, 2, 3, and let's call that Q prime, and Q double prime, Q prime. Again, it will be the same ratio, just like we have seen here, that ratio for this, they are in the same ratio, just as the ratio of this to this. That will be the same ratio as the ratio of this to that one, the same ratio as the ratio of this, that. That is based on the theory of similar triangles. Now, suppose now we have a real system. Suppose now we think of a real system. Let's think of a real system. And the best one for illustration, we can use the acetic acid, chloroform, water system. So we have the three components: acetic acid, chloroform, water system. So let's have our system. Use some more space here. Acetic acid. That's acetic acid. Chloroform. That is chloroform. Acetic acid. And this is water. Now, pay attention. The first thing which you got to know is chloroform and water are not miscible. We have talked about immiscible systems, partially miscible systems. So chloroform and water are not miscible. So if we have 0%, because remember we said this is 0 and that's 100% acetic acid. This is 0, that's 100% water. That is 0, that's 100% chloroform. Now if we have 0% of acetic acid, then we will have two conjugate solutions, M and N. We'll have two conjugate solutions, M and N. And the mixture, the resultant mixture, you have that composition there. Let's call it Q. These are two conjugate solutions. Remember, chloroform and water are not miscible. So they form two conjugate solutions. Two conjugate solutions. We talked about these systems when we talked about the upper and lower consolute temperatures. The upper consolute temperature in the water phenol system. We talked about the lower consolute temperature in the water triethylamine system. And we had a system which had both upper and lower consolute temperatures where we are dealing with nicotine and water mixture. Now, these are conjugate solutions. And at this particular point, you can use lever principle. There are lectures which you have done on lever principle. I encourage you to go through those lectures for completeness, so that you will find that using the lever principle, you can tell the relative amounts of N, and M, just from the length of the segment. The length of the segment. This segment here, MQ, represents composition of amount of N. This segment here, QN, represents the composition of M. Now, as you continue increasing, putting in acetic acid, we will get a profile which will be like that. And now we will find that this will be probably M and N. Now, if you look at M and N there, it's not as a horizontal tie line. If you try to do that tie line, you will see that it is not, it's skewed, displaced through some angle. Displaced through some angle. And that's very simple. The reason for that is very, very simple. Is that acetic acid is being preferentially dissolved in the water layer. And that causes that asymmetry in terms of the concentrations of the conjugate solutions. I repeat, acetic acid is soluble in water, so as you increase the amount of acetic acid, it is preferentially dissolved in water, and that causes this asymmetry which you are seeing here, so that you don't have M and N exactly horizontal. Very important for us to note that. And as you continue, you will reach a point here. This point, let us call it point Z. At that point Z now, the two conjugate solutions will have the same composition. The two conjugate solutions will have the same composition, and that's referred to as the Plait point. So just note at the Plait point, the two conjugate solutions have the same composition. Mn have same composition. Just note that. That point, they have the same composition, is referred to as the Plait point. It's referred to as the Plait point. Now, let's just say, suppose we have two immiscible systems. Suppose we have two immiscible systems. Suppose we have two immiscible systems, A, B, C, so that this one here, we have a Plait point at that point, another Plait point at this point. Those are Plait points. And don't get the notion, don't get the idea that the Plait point must be on the binodal curve. No, it doesn't have to be on this binodal curve. This is just for illustration purposes. The Plait point can be anywhere outside this binodal curve. That's a binodal curve. So, if we have two Plait points here for these immiscible components, we have this immiscible, two immiscible systems. If we lower the temperature, then theoretically we expect that the two can fuse. Those two can fuse and merge, and so we will end up with a band. We'll end up with a band. If lower temperature, the two Plait points will converge and will form a band. That particular point. In summary, first, you must know what kind of phase rule you're dealing with. We are dealing with phase rule where now we have three components, and we said it is F is equals to C. That is three components minus P plus 2, that is 5 minus P. And so even if you had say one phase there, then it means you have 4 variables. And so it should not bother you, because one of the variables will be pressure, temperature, mole fraction of 1, mole fraction of 2. Those are 4 variables. So we are both pressure, temperature, and composition variables. So you must get your phase rule right. Whichever, if you keep the temperature constant, then you know you have to subtract 1 from the 2 representing temperature and pressure. If you keep pressure constant, do the same. If you keep pressure and temperature constant, then you subtract those 2 and you know what your phase rule is. And you have said you can represent them, the Gibbs-Roozeboom triangular representation, and that's an equilateral triangle, and we have seen how we mark the amounts of each of those components based on segmentalization of this triangle, where we treat that as 100%. We can mark the 0% to 100%, and the same with this component, and the same with that component. And we are able to see that if, for example, we have a mixture of 2 components, then if you have a mixture having 2 state points, the composition will fall on the line. If there are 3, it fall in the triangle, and you can use the theory of similar triangles to show that the relative proportions along that line to that apex which we've drawn are the same. So thank you. We'll pick up later.